No, I'm not going to mention the theme now. I'm just going to present the problem. Okay, and that will be more interesting. So this, I'll just say subset counting problem. Can you see this? Can you guys see the screen? Yes. Okay. So subset counting. Subset counting problem. Okay. So let's first do the most basic version of this question. That is, let S be, or let me just use the official notation. Maybe I can say this. This basically denotes the set of elements from 1 to 10. But for us, the elements don't matter. How many elements are there? Only that matters. But this is the set. So what are the total number of subsets? What is the total number of subsets? Right? What is the total number of subsets? Can anybody quickly give an explanation for this? I think this is all of us would know, but let's see. Yeah, let's do this. Or maybe if we don't know, then it's even better. We'll learn a new thing. Okay. So what's the total number of subsets? So example of some subsets would obviously be the empty set, right? And you have singleton sets, you want, and then you can have this size 2 and many, right? How many of them are there? Right. The set itself is certainly there. Yeah. So how many will be there in total? Right. So the answer is 2 to the power 10. Okay. This is a rather well-known fact. But how do we prove this? How do we, say that this is the answer? Yes, absolutely. It's just based on the fact that every element has 2 choices. Okay. So the main thing is every element has 2 choices. Every element has 2 choices. Okay. And let me just leave it at that. And now I would suggest all of you to write this. Okay. Even if you find it very easy, you can just try to write this. Okay. That why exactly are we multiplying and so on. Okay. But yeah, this is something that all of us know. Obviously, there are not so good ways to do this also. Number of subsets of size 0, size 1, you can do casework on this size and you can add them up. But yeah, that's not such a good way to do, but it gives you an identity. So this is fine. Now, if you have ever seen this type of question, or you're seeing this now, what's the next natural extension of this question? Okay. So what is a natural extension of this question? What is a, or it's just a natural variation, right? Natural variation. What could be a natural variation? Well, a very simple one is total number of subsets of even size. Yeah, this is just a natural variation, that you can maybe have ask yourself or something. Okay? Just a variation. Let's try to answer this. So this is the variation, and let's try to answer this. So we are looking for subsets with even size. Even would obviously imply 0 also. So here examples would be empty, size size 2, size, so on, right? Size 2, size 4, and so on. Just think about this. So first, maybe just try to maybe give an answer. If you think you are closer to that, just an answer and maybe a rough explanation would also do first. And then obviously we'll do it proper rigorously also, which. Okay. So so now that's a guess you make, right? So rather than me saying it, can you back it up with more explanations or yeah. Yeah. Okay. So you're saying that there is some sort of symmetry. Symmetry between what? So there is a symmetry between sets of even size and odd size. Maybe that's what you have in mind. And when you say half of the total, that's what it means, right? But that is also, both are even. I'm just calling it even sets. But your idea of pairing makes a lot of sense. Pair even sets with odd sets. Okay, so let's keep, yeah. Yeah, so let's think about this. This idea is good. Why is it the same for everyone? Oh, then maybe you can refresh your, yeah, yes. So currently I've drawn two blobs also, one even and odd, one referring to odd. So there is 5, there is this. So this symmetry, for all of us, we can also understand the symmetry. Like before we approach this pairing, if you directly get the pairing, then that's wonderful, obviously. But if you want to be more confident of this answer, then small cases will tell you that it is correct. Okay, so do small cases to certify. I mean, I'm not saying, okay, not certify maybe, but just to be more sure. Do small cases to be more sure. So that is something that you guys can quickly do. And you will see that the answer is always, half of, if it's 2, then it's half of 2 to the power 2, half of 2 to the power 3, it's just 2 to the power 9 and so on. So from here on, I'm taking it, I'll take it that everybody can feel intuitively that the answer is half of the total number of sets, right? So number of even size sets is total subsets total number of subsets divided by 2. Okay, if anybody doesn't see this intuitively, like roughly speaking, like because even is not special than odd, right? And you can take some small cases and you can verify that it is always coming out to be half. Now the job is to prove it. There is one idea here about symmetry and pairing that you guys can try, or there are other ideas. So let's give ourselves some time and think about this. And maybe you can do it with other ways also. But if this was an MCQ, then you would already know the answer is half. Okay, so that is just a small point. Okay. So anyone has made any progress? Maybe based on this pairing idea, how would you pair given if I give you an even size subset, how would you what would be a natural way to associate an odd size subset to it? Right? Hmm. Right. Anyone? Why are we pairing? Yeah, that's a very important question. That why are we pairing even with odd? That's right. Yeah. So we are trying to show that number of. So just saying that in another way is just yeah, number of even size subsets. We are trying to say. So we have got the intuition that they are equal, but they are equal. Sorry, we've got the intuition that the number of even size subsets is half, but really they are half because the number of even size subsets is equal to the number of odd size subsets. So we basically want to show that these two sets have the same size. Okay, so we are trying to say that these two things have the same size. And a natural way to do that is to pair the things, right? From one piece, from the collection of even subsets and the collection of all subsets, we develop a pairing. Like if you can pair the elements, then you know that the size is same. This is a very powerful way to show that size of two sets is same or two collections is same without actually knowing their size, right? And obviously, once we know that they are same, then we'll also know their size because both of them will have size. This was the idea that we had used last day, right? Where we still don't maybe know. Some of you may have done it or read it, but it's good. But it means a priori, we don't really know what is the real answer to those questions we did last time, right? But we did show in some mysterious ways and some funny ways and some interesting ways, right? Right, different ways, right? To show we showed that the different things we were looking at had the same size, but we didn't even know what they were, but we know that they were same. That is the idea of pairing. So now the question is, what is the way to pair? What will be a natural way to pair the things? We want a natural way, right? We want a prescription. We want a way to describe that, right? Rather a description, right? Yeah. Okay, consecutively. So how can you go into more details? Sorry, a pair of? Yes, but in what way? Like, what will be the exact rule? Because otherwise, whether it's a pairing or not, we don't know, right? If something will be left over on this side or that side, we won't know. Because total number of size 2 subsets is not same as total number of size 3 subsets. So if I just pair this, then it's not clear how is the pairing, what is the rule. So let's take a small example. Let's take a smaller example. Let's say that there were these three. Let's say that we were looking at this set. Okay. Now, you also obviously know that the answer will be 4 in this case, but the point is to develop an intuition to know how the pairing would be done. Right. So now let's think. Now we have explicitly written all the items of interest. Now, how should we pair? So that the pairing, so that the method of pairing is same for all the elements. There is one rule that we can apply to all the elements in a uniform way. But let's just think freely. Let's think how can we pair this to the two sides? I mean, I can obviously just say, I can obviously just write like this. But then what is the rule? I must know a rule, because if I don't know a rule, then I cannot extend this to larger cases, right? Because yeah. So I cannot, what I cannot do, for example, I cannot say pair the size 2 subsets with size 3 subsets, right? Because that does not work. Because if I pair like this, then what about these two? Now, if you say, okay, pair these two with size 1 subsets, but then what's the rule? If there is no proper rule, then how would we know? I just okay. So let's say as a way to start, let's say if I maybe a small example will be giving and a pairing will be given to you, and then you will have to predict the rule. Okay, so I'm not going to tell you the rule. I'll just say the pairing. Okay, for this small case, and then you have to predict the rule. At least. Hmm. Okay. 3-element group. Like this one, you mean? Okay. 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 So you're saying that. So are you saying that the size, that size two things we are matching with size three or size one, not with size five? No. The total to be the least. Okay. So you want not too many differences. Okay. Uh, okay. Okay. That makes, yeah, yeah. Yes, certainly one of them will be a subset of the other. Yeah, that's another feature. But again, these two, both the points that have been mentioned so far, do not yet give us a rule, right? A clear rule, right? A simple rule, maybe I can say. It's vague. Yeah. So how you would make a unique decision with that for higher cases is not so clear. Okay. So let me do one thing. Okay. Let me just make a, I don't know, will that be useful? No. Yeah, but we have to really discover it, right? Otherwise, there is no point. So let me, yeah, because this is maybe a new type of example. So unless we actually know it, if I just give it to do later, it's not so useful maybe. Yeah, so let's actually do, so let's do a bigger case and let me keep this pairing over here. Let me remove all these words now, not so useful. Nobody's reading this word now, surely. So I'll go with 4, okay? Because I really want you guys to maybe see the rule because that is important. Because if you can see it yourself, then you would never maybe, then you would just take and it's useful. So let's do for 4. So this will be slightly bigger. And maybe you can see because we need a more clear rule. So obviously there is empty here. Three, but now you have 1,4 also, 2,4, 3,4, 6 already. So so we have size 2 and size 4. Am I missing something? Yeah. 4, 2,4, 2,3, 2,1, 3,4. Wait, 1,3. Yeah, yeah, 1,3 I'm missing. So 1,3. Okay. And so now maybe you guys can already start thinking about what should the pairing be. And I'll also write to do a pairing. No, so I should first. So I'm randomly drawing these, writing these. Now these collection of subsets have very interesting structures. We have seen a few bit of that in partial orders class, but that's not useful here. So I'm just drawing it in a random way. Okay, maybe it is useful, but that will just get technical thinking, not very useful. This is all right. So I will do a pairing. So what should I pair 1 comma 2 with? So 5 I'm pairing with 1. I suppose that's clear to all of us that it should go with 1. Natural choice is going with 1. Because see, if I pair it with 3, then it will not really be a different pairing. It will just be looking at, because 3 and 1 are the same things, right? These are both single. 3 can take the place of 1. There's no addition happening here. But let me just pair 5 with 1. Now what? So where should I pair 1 comma 2 with? Okay, so let's pair it with 2. Yeah. Now a good way to test yourself from here is that you should ask us the next thing, because if your pairing is good, then it will keep giving us the right ways, and we won't end up in a problem in the end. So now with this, whatever we have said, where should we pair, what we should be paired 2 comma 3 with? Okay, so if you pair with this, so at this point I don't know if this is right or wrong. Let's say I do with this. Now we'll see where should we pair 1 comma 4 with. Okay, okay, so okay, then 2 comma 4. Okay. Okay, so Ishana, since you're saying this, would you have paired 2 comma 3 with 3, or would you have a different choice? Maybe because if one person says, then maybe we can, he or she can tell the rule. Where would you pair 2 comma 3 with? Are you okay with 3, or do you want to? Okay, so you're saying 1 comma 2 comma 3. Okay, so let's see if this one is correct. Then we'll come to the other choice also. Okay, so I'll let you finish then. Where should you pair 3 comma 4 with? Okay, so I think you've got the rule. What's the rule? Or you can say for the rest too also, remaining ones, if you want. Sorry, can you say that again? For 2 comma 4, you are putting a 1, right? You seem to be putting a 1. Yeah. Why? And so for 1 comma 2, why are you removing the 1? Or for 2 comma 3, why are you putting the 1? Maybe you can just say the rule again. Yeah. Okay, okay. But your choices seem to be correct. Like correct in the sense that, okay. Okay, so where would you pair 1 comma 3 with? Okay, that would be, there's no other choice than 3. And for this, it is this. Okay. So this is your pairing. Can anybody, okay, before we go to the other people's pairings, can anybody give a reason to this, logic behind this? Maybe that's not a very good question because. Hmm, 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 hmm. Which number? The number 1. It's yes, yes. So that is it. That's perfect. That's all. That's all we need to know. That's right. And here we have taken 1 as the pivot, kind of. Right. We are shuffling with 1. Absolutely. So this side is add a 1. And see, 1 is not special here, but we treat 1 as special, but that's not the point. Someone could have treated, someone can treat 2 like that. I'll add a 2 and remove a 2. But that will give the same answer. Yes, yes, exactly. Yeah, exactly. So, but that will not make any difference. That's right. So this side we are going by adding a 1. Adding a 1 means if some set does not have a 1, you give it a 1. And this side is right. Okay, I should not say that. I should just adding a 1, adding or removing a 1. Sorry, this is not a good way to write here. I should say adding or removing. And it's very clear. Adding or, and you can see that the same rule works on this side also. Okay. Now this is not vague anymore. Right? This is a precise version of what was said earlier. So what was said earlier was not wrong, that I don't want too much change. Okay, so it's like I want to change by only 1. And this is exactly what's happening. This is changing by only 1, and the change is exactly with the number 1, number 1 only. Okay. And now it's very clear that this is the pairing. Okay. Write a reasoning. Write a reasoning for what? For the fact that this is a pairing. Okay. Like you must say very clearly that if a set here is paired with something, then that will get paired with this only and nothing else, and so on, right? 2 things should not get paired with the same thing. You have to write all this. Pairing means that 2 things should not end up getting paired with the same thing. Okay, so please write it. Okay, especially if you have already started writing proofs, those who are especially grade 10 and above, we should definitely write a proof, but all of us should try. Okay, but the key is to see this thing. This is the pattern. This is the thing. It's a natural pairing. Okay, a natural pairing. This is just a word I'm putting here. Yeah. Is this only one? I don't know. Are there some other descriptions, other way to describe, other simple rule, very simple rule like this? Obviously, you can say add or remove a 2 also, but I'm saying different kind of rule. I don't know. You can think. Okay. So that's a interesting thing. And then that answers our question, right? Now, if I remove this with even sum, okay, do this for homework. Okay, think about this. Okay, please note it down, do this for homework. It's very similar to what we have done. And yeah, sum is even. So you want sets whose sum is even. Okay, so this will not work. The sum is here is odd. 1 plus 2 is odd, but this will work. So it's not based on size, but it's based on sum. Okay. So yeah, that's one question. And this is also called, so this is A and this is B. What we have done is a natural pairing. So a natural pairing is also called a bijection. All these words are useful because it helps you to think clearly maybe sometimes. And also, you're reading books and in exams also. So a natural pairing is called a natural pairing, or just a pairing basically, is called a natural bijection. These are the same thing. Bijection and pairing are the same words. Here, you can see the same rule applies. If you follow the same rule, it will also work in this. Right? If a set does not have a 1, we give it a 1. And if it has a 1, we remove it. 1, 3 has a 1, and so 1 gets stripped off. Right? Remove a 1. I see -1. Not -1, but it's removing a 1. Right? And you see, if something does not have a 1, we give it a 1. So the rule, this one rule fits in all of them. Okay. Okay. Now try to apply the similar idea or different idea even better to this problem of even sums. No, if it doesn't have a 1, then you give it a 1. Mm-hmm. Mm-hmm. Anything. See, you see, actually anything will work, right? Yeah. Because this set does not know what is 1, what is 2. It just knows there are two different things. Mm-hmm. Yes. So here also similar thing works, but what exactly? Okay, let me think. Uh, yes, yeah, similar thing works, right? Adding a 1, yeah. The association actually will be exactly the same, but let's keep it for, yeah. You also try to write it, but yeah, it's very similar. It's exactly the same actually. Yeah, is that right? The rule is exactly the same. So yeah, so these problems actually. So another observation is that these problems actually do not depend on the exact set. They just depend on the think that a set with 10 elements. Maybe a question will be set with 10 elements. It will not say this set, but because you are only interested in the number, it doesn't matter number of such things. It doesn't matter what is there inside the set. So you can take 1, 2, 3, 4, 10 because this is easy for us to think. Obviously, for the even sum question, it has to be numbers. I can't have cats and dogs there, but otherwise I can have anything there. It depends. I can decorate the set as is convenient for me to give a meaning which will help me to describe my rule. Yep. But anyways, all those points we'll see. So we had this natural bijection. Okay, but here is another observation. So you can try this later, but this is an interesting thing which you can think about. What's the total number of subsets of even size? Let's come back to this question. So we know now that the answer is, because 2 is such a number, right? That it becomes 2 to the power 9. We know that the answer is 2 to the power 9. Okay, you guys agree, right? The answer is 2 to the power 9. But then what do we see? We learn a very interesting, maybe we already know it, but we know that this is also equal to, we also obviously know this is also equal to total subsets of, for example, obviously, yeah, that's right. Obviously, this is also total subsets of, as Pragya said, it could be 1000, 1001 till 1008 also. It's that also, but to put it simply, it is total number of subsets of this. So we are seeing that, let me write it like diagrammatically, total even subsets. So total even total even subsets of this set, again this big bag, is equal to total subsets of the previous case. Okay, now this is a two big bags. Now we know that the answer to both is 2 to the power 9. Okay, so someone who knows numbers and so on, they have no problem. Maybe means computationally we are done. Okay, logically we are done. But it would be very beautiful and very useful for other places if one can again show a natural pairing. We have not shown this. We have shown a natural pairing between even subsets of this 10 till 1 to 10 and odd subsets. That natural pairing we have seen. But can anybody show a natural pair, just like we developed a recipe to pair those things, right? Can we do a pairing here? And this is a very interesting question, and I have never thought about this before. Okay, so if you can think about this and write an answer, then that will be your own new thing. Okay, so a natural pairing, please think about this. Now this is not so easy. The pairing we described earlier will not work, right? Because the size can increase, but here we want the size to only go down. Okay. So I don't know. Think about this. First, just see if the question is clear, and then you can think about this for homework. So you see what's happening, right? You need to get all subsets of 1 to 9. This is all subsets of 1 to 9. And this is only even subsets. How do you match them? Our previous rule will not work directly because that will only give you odd subsets on that side. Okay. So we know that there is a pairing, but we don't know if there is a natural pairing that one can get through a rule, simple rule. So is the question clear? If it's not clear, you should ask. Yes, yeah, right. So see, first thing we know that both these sets have both these collections have the same size, right? Both have 2 to the power 9 size, right? Total subsets of 1 to 9 and even subsets of 1 to 10 both have the same size. We know that, but can we establish that fact by a natural pairing? Okay, so I want a rule just like we did previously. What kind of rule we had? So we had a natural pairing which takes an even subset of 1 to 10 and pairs with it an odd subset of 1 to 10, right? So we had a natural pairing of, right, and we paired it with odd. This pairing we naturally had, and that helped us to show that the size is both 2 to the power 9. But now we also have discovered that the size of these two is 2 to the power 9. But now we are just for, maybe you could say on one level, just for fun, we want to know if a natural pairing here, there is a natural, so the natural pairing here is not needed, right? If you're just interested in the final answer, okay, it's not needed, but it would be good to see. Okay, so for example, because it just looks very good, right? If you have a natural pairing, see, a natural pairing is more than just numerical equivalence. Isn't that true? Right? I mean, a natural way to pair two sets. Isn't that's much more more, yeah, exactly. Something is more organized. The final answer is the same. Final product is the same, but it says much more. Right? It says that there is a natural way to jump from one side to the other. Right, and that can be very useful because this art of showing that two sets have the same size can be very useful, right? Because sometimes you may not know the size. Yeah. And it's just very elegant, simply put, some natural. But I don't know what that will be. I actually don't know. For example, if you have this, then where should you pair this? Should you just leave it as it is? I don't know. Or if you have this, then where should you send this? Same sets? Yes, yeah. There are. Yeah, right. There are a lot of same sets on both sides also. So should you match them to themselves or should you shuffle them or not? You have to think, but you have to describe a rule, an interesting rule that pairs them. Think about this. This is homework material. So just write it down, then we'll move to the next thing. Yeah. Okay. So let's move to the next thing. Yeah, so let me not do more about this subset counting today. Today we just saw the applications of, then just saw this, this art of showing bijections between two things. Okay, let's move back. Yeah, so the last, so maybe not last class, but last to last class. Okay, we saw this thing about triangulations. I just say that again. Triangulations of a convex polygon, just polygon, regular polygon. But yeah, convex polygon. So number of triangulations, right? For example, if you have a square, then it has two triangulations. Sorry, if you take a square, okay, I'm saying a square. Actually, the exact the regularity doesn't matter. It can be rectangle also because this is a combinatorics question. It doesn't really depend on things like length and width and so on. So in any case, but we know that there are two triangles. Now, what is a triangulation? Triangulation is simply, as you know, is just the partition. Means there should be no overlap of my thing, of my polygon into triangles. Now you obviously know how many triangles are needed and so on. All that you have done in elementary things, n minus two triangles and so on, right? But how many triangulations? So here we see two triangulations. Now these we are calling different. Now if you say I can rotate one and go to the other, that's very good. But these we will consider different. You can assume that this is a labeled thing and then they are different. So if they look different, they are different, okay? Yeah, so we are not asking for isomorphic ones, then it becomes very difficult. But these two are obviously different. This is for square, it is 2. Now we saw that for example, hexagon and so on, right? So we can take a pentagon. For pentagon, I think we had got 4, right? Let's do it. We can do it now. 4 triangulations. I have to copy paste. Now there's no copy paste here. That's a very strange thing. So let me just draw it with hand. Okay? It doesn't really matter. And we are not kids, so it's okay. I mean, we are used to these things. Okay. So how many triangulations will we get? Now we had done this in a very strategic way. Yes, with diagonals. Yeah, basically diagonals, that's right. And so basically there is only this type of thing, right? Yeah, so there will be 5. You are right, not 4. They're not 4. Yeah, there'll be 5. So it's basically not, so it's not as difficult as it looks in the beginning, in the sense that once you find one kind of triangulations, you can just use that and run with that and get all the different ones. So we had seen that this is answer is 5. Now something very interesting we are seeing is that these numbers again again come back to the same story. This is 2, this is 5. So we have already done many problems. Okay, so this for hexagon, I'm not doing this, but last time we did this. Okay, so let me not go into the details and let me just draw the main types. So this is one type, and maybe someone can fill in the blanks. So I'm just drawing the different types. I don't want to draw all of them. This is another type. And there was another type. What was that? Right, exactly. Right. Triangle. So how do we draw like this, right? Yes, absolutely. So you see, these are the 3 types, and you can understand that for this, I think there will be 6 ones. For this, there will be 3. For this, there will be 6, because you can go the other way also, I think. Okay, but anyway, there will be 15 of them. Okay. So now the point of all this is that this pattern that you see here, this is once again, we have already seen these numbers. Okay, if you look at okay, let me be very precise, otherwise this will become a mess. Yeah, let me be precise. Now, obviously you guys have already seen these numbers, this pattern, but let me precisely say what is the exact thing I'm interested in. Yeah, otherwise we might end up. So see, first of all, let me mention this. These numbers 2, 5, 15, and the next will be 42 if you have done the homework. Right, the next will be 42. I had asked this to do this. You can do this for a heptagon. It does not take too much time. Don't think that it will take so much time. I don't want to know. Just draw a heptagon, find the different families, find the different types of triangulations, you will get 42. It's not too big. Or is it 15 or is it 14? What was it? 15 only, I think. It was 14, right? I think I'm written. Oh yes, we don't have 3 ways, right? We have 2 ways, right? That's why it's 14. So why did I say 3? There is 2 ways, right? Because you can choose these 3 or you can choose the others. There are 2 ways. That's perfect. So it's 14. Good. Thanks. This 14. So these numbers we have already seen. We have seen this in several problems. Okay. Let me not mention all of them. And those problems, you have already seen the connection between those problems. Maybe I can say that now in the sense that what connections we saw. So last time we saw that, let's say, for example, number of paths of length n from 0, right? This thing, right? And not visiting 0 before, not visiting earlier. This problem we saw. Now we had reduced this problem to number of paths of, well, only on the positive side we had said, of length n minus 1 from 0 to n minus 1. Now what length n minus 1? Wait, 1 second. Yeah, length means steps, yeah, of n steps. No, so that was, what was that? That was 2n steps, not n steps. Yeah, 2n steps. And this would become number of paths of 2n minus 2, 2n, 2 times n minus 2 steps from 0 to 0. Yeah, where not allowed to go on negative side. So you can come back, but not allowed to go on negative side. Negative side. We had seen that these 2 problems were the same, right? Because if we're taking 2n steps, the first and the last step you can remove because that is, and then it becomes like from 1 to 1. Actually, I should write 1 to 1, but then that's the same thing as 0 to 0. Doesn't really matter, right? So we had seen these are same, okay? And then we kind of saw that this is same as number of legal parenthesizations, right? Because you have to start at any point, you're not allowed to have more close bracket. This is like at any point, you're not allowed to have more left moves. And so they were all similar questions, right? And then we saw binary trees and we saw there was a connection with them also. Given binary trees, we can connect them. All that we saw. But we are not able to see a connection with this problem with the others. And we had many other problems which we had done in the earlier classes. But this problem, we have not yet seen the connection. We have seen the pattern, but we are not able to describe the connection. Okay. So today I want to describe the connection of this problem. This is, you can see, but I want to connect this. So there is a need to connect, okay, in the sense that this is being signaled as already. Okay, and we want a very neat connection. So I'm going to choose the connection with trees. Okay, for a certain reason, because it will give again a new type of bijection, which you may not have thought before. Okay, so yeah, so we'll connect it with complete binary trees. This is again, you may ask, why are we doing this? Why can't we just count this separately and count this separately? Well, number one, it is not so simple. And number two, just counting separately and knowing the answer, that's okay. But seeing a direct connection, like given this thing, can I directly match it with some certain kind of tree with a certain specific rule? That's much more elegant, much more, tells you more, is better, right? So complete binary tree. So let's first start doing this again. Complete binary trees. So let's do a bit, okay? So let's say we want complete binary trees with 2 leaves. 2 leaves. So let's not do the 1 leaf case. How many of them are there with 2 leaves? How many complete binary trees with 2 leaves? Only one, right? There's only one. There's no other, right? So with 3 leaves, so before you say, so very, yeah, there will be 2, exactly. And just a very quick way to say, like you can say that which level, so this is level 1, this is level 2, and you can say left child or right child. Okay. Or you could say the number on that level. Yeah. So obviously here at the second level, there will be only 2 things. And then it's very simple. You can either do this or you can do. So remember, we are not labeling the trees. If you label the tree with numbers, you can shuffle the numbers, you can create maybe more trees. But we are not interested in that. That will give a different answer. We are only interested in trees like this. Okay, is this okay or is this wrong? Is this correct what I have drawn? Which one? Yeah, that's why it's wrong. That's right. It's wrong because it represents 1 children. It should be 2. That's why complete. Complete means that every vertex or every node should have 2 children or no children. Okay, it cannot have one going downward. So that's why it's wrong. That's why these are special trees. Okay, these are not some, and these trees, as we already saw, they represent computation. They represent, the sequence of ways in which some n variables are calculated. Okay, so these are not, obviously these are very interesting on their own, but they have a lot of use also in that sense, if that means anything. Yeah, so these are 2. Now, these are different, okay, because here we say the left one, here we say the right one, here left and right. So here the left child has a different tree below it, here the left child has a different tree below it. That's why they're different. They're different trees. Now on some level they are the same trees. In some context they are the same trees, like some context like isomorphism. If you're not interested in left child, right child, and so on, if you're just interested in it as a graph, then what's the difference between these 2 graphs? There is actually no difference, right? In some level. But yeah, but if you want like left and right to be different, for example, if you want to do calculations, then obviously they become different, right? So then you have to consider them different. So for this purpose, we are considering them different. Then there are 2. So here there are 2. Let's continue. Sorry. Five leaves. No, why 5 leaves? 4 leaves. So how many will be there? Maybe you can do this together quickly. So this. Yeah, so there are 4, exactly, that's right. So there are these 4 ways. I've drawn 3, I think. No, the 4 already, 4 we will get, but then you can flip these, right? You can get 5. Okay, 2 more. Basically, you can flip them, So there are 5 ways. Now, again, there's the same numbers. Same numbers, right? So this number is this. With 3 leaves, you get no. So 2 leaves is not in this, and that will be okay. That will correspond to triangle. So that's not so bad. Right? That will be triangle. So let me remove this thing. For a triangle, there will be 1, right? So 2 leaves is the case of a triangle. So this is with this. The 3 leaves, it goes to square wala case. With 4 leaves, it goes to this, and then you can similarly work out with 5 leaves. it will be 14. Okay, you can, and it's not so difficult. You can just basically you can build from the smaller cases, right? You can make one child and you can do this 5, you can attach these and you can do the creatively, you can do. It's not so difficult. So there is a clear connection. Now explain it. There is a big explain written here. How do we explain this connection? Without knowing the answers. Without knowing what the actual answer will be for, let's say, n equal to 100. And we don't know already. So basically, these two problems could look very, very different. But can you show a similarity between these two problems, which will maybe at least give some intuition as to why the answer are coming out to be the same? But what is it? Certainly it has to do with this shape, because if the shape was something random, then you would not get this answer, because yeah, total number of trees is something very different, n to the power n minus 2. To what? Yeah, exactly. I need some answer which connects these two things. Yeah. Okay. But the two diagonals, but in general, what's happening? There is have to be some similarity in general. Yes, it's again, two children is important because otherwise this will not be true. But what is the connection between these two things? What gets us closer to the truth? Closer to and knowing that these are actually same. So one way to feel this, and that will not be an answer, maybe we'll make it an answer and we'll actually use that to connect the things, is that these two structures grow in the same way. Now I'll explain that. This is not an answer, okay? But the point is that both grow in the same way. In the same way. Now, what do I mean by this? See, if you want to make a tree with, let's say, if you want to make a tree with, let's say, 6 leaves, then you will start with this point, and you'll make 2 trees, right? Then this will be a tree with certain number of leaves, right? That part, the left child children, and this will be a tree with some number of leaves, right? Some A leaves, and this will be 6 minus A leaves, right? I mean, the A could be 1 also, or the A could be 5 also. Okay, just like you can see in this, if you wanted four leaves, then this is 2, it's broken into 2 and 2, or it's broken into 3 and 1, or it's broken into again 3 and 1, or this will be broken into 1 and 3. So we are breaking 4 into these several ways, and that's basically we are using the smaller case only to attach and get the bigger cases. That's the way in which the right side grows. So I've described sort of a differential equation for the right side for those who have done it. But otherwise, you understand they grow in the same way, they change in the same way. And this will actually make it precise by a recurrence relation, which is what the differential equation of combinatorics is. Okay? They grow in the same way. I mean, I've only said how the right-hand side grows. Now, how does the left-hand side grow? Suppose you have a big polygon. Let's say again 10 sides, okay? Or 6 leaves. So 6 leaves will correspond to 8 sides, right? 8 sides. So let's actually make it Now I want to show that this also grows in the same way. So you can mark this one. Now you see, I will decide how to distribute the six leaves basically means 6 triangles, right? 8 sides means 6 triangles, right? That's what it means, right? 6 triangles and 6 leaves. Now, how am I going to divide them, right? So basically first, now hold on. Am I making a mistake? This is 6 corresponds to 14 and the 14, no. So that's wrong, right? Yeah, 6 sides answer is 14 and that corresponds to 5 leaves, right? So 6 leaves will correspond, so 6 leaves wala case will correspond to 7, right? And so this means 7 leaves. This will be corresponding to 7 leaves. Is that right? This will correspond to 7 leaves, but that is not important to know. Point is that again, I'm just going to decide what triangle I'm going to make on base 1, 2. If I suppose, for example, if I make this as one triangle, okay, can't make that. I'm sorry. What am I doing? That's not important. If I make this triangle, then what have I done? Then I have broken the problem of this 5 triangles. Basically, once I make this triangle, now I have 5 more triangles, right? Then the problem breaks down to this smaller case. Now I have to divide this into 4 triangles, and this one into 1 triangle. Okay, this is one way to break it, right? The other way to break it, the other way in which it will come from a smaller case, you can see, if I have this, and on this main front, I'd say no, I'll make this triangle. If I make this triangle, then again I have 5 triangles, but now I'm distributing them as 2 this side and 3 this side. So basically, again, the problem is to break a quadrilateral into 2 triangles, and this side it is to break a pentagon into 3 triangles. So you see, once again, I'm reducing this thing to smaller cases in the exact same ways that as I would do for tree, right? If I wanted a tree with 5 leaves, or sorry, if I wanted a tree with so how many leaves would this be? I mean, any number of leaves, right? If I want a tree with this is for 5 leaves. 1 minute. 8 sides, no, 8 sides would mean 6 triangles, right? Yeah, 8 sides would mean 6 triangles. Okay, but after I make 1 triangle, I'll be only left with 5 triangles. Right? So, okay, so forget about the leaves thing now, but 8 sides would need 6 triangles, right? And once I make 1 triangle, I'll be left with 5 triangles, right? And so basically then I have to divide that 5 into 2 parts. Okay. How I divide it will be based on how I make the first triangle. The first triangle is a triangle with 1 and 2 as the base, as one base. Then the problem breaks down to smaller cases. But this is something similar that happens in the case of trees also. Let's elaborate this once again. But this is not an answer. This is a road to a recurrence that we will see later on, but not now because it's a little complicated. And that will not actually tell us, it's not a direct connection even. It's just it will tell you the answer is correct. I mean, the answer is same, but see in the trees case also, so 1 minute, yeah, it doesn't really matter. Let's say you have 7 leaves. Okay, then here also, right, you would make cases, right? You can make case like this side has 6 leaves and this side has only 1 leaf. Just like this side has 1 triangle and this side has 4 triangles, the remaining, right? Or 2, 3. Here you can again make 2 leaves and here the remaining 5 leaves, right? So just like depending on the left subtree and the right subtree, how many leaves they will have, we can do casework on that. Here also, left quadrilateral and right quadrilateral, how many triangles we'll have. So the way in which it breaks down to smaller cases is the same. Or I can say the way it is built from the smaller cases is similar in both the problems. So both the problems kind of grow in the same way. Is that intuitive? This is just an intuitive argument. It's a rough argument. We are not yet in a position to make this precise. I can cram that. I can try to say that, but it will not be very. This is already a little involved. But yes, once I introduce a language of, once we say it in terms of recurrences, it will actually be cleaner also. But I just want to leave with this intuition now. So is this fine? They're growing in the same way. Kind of the way we break them down into smaller cases is kind of similar. So yeah, so this is just on an intuitive level, but we want to actually see a direct, but this will never tell you the direct pairing, the direct natural pairing. It doesn't tell you the natural pairing. It doesn't really tell you. This gets very convoluted and yeah, but it's very interesting showing that things are same. But we want to see a natural way. So what we want to do is we want to actually do like a super proof kind of, okay? And it's not my idea. It's a very interesting idea and it's used in a lot of places in different other ways. We'll see more so in discrete maths is used. This was a new idea. I don't know who. So this I am seeing from Stanley's book. I had seen. Let me see if they had mentioned the reference that time. Or has it gone into like the folk? So it's like folklore, like they don't know the source. No, so they don't have the source. They just give the bijection. Yeah, obviously I remember it because I had seen it long time. Once you see it, it's hard to forget it. It's so nice. So yeah, so the book is a little advanced. That's why it's hard to read. But I'll share it. I'll show you from the book also. But this is a completely non-original thing. It's not at all. I could have maybe never thought of this. Okay, so maybe you guys can try to put some reason in it. Yeah, so this is one of the things which I actually don't know how it happens. But then yeah, not everything you can. So we want to take this now. We want to take a triangulation. Okay. So like last time, last time we had a tree and we had those parenthesizations and evaluations, right? Then from the evaluations in a natural way, we could go to a tree, right? And from the tree, we could come to a evaluation in a very natural way. That's how computation happens, the way we had shown, right? For example, if we had like, let's say A, B, C, D, E, F, and let's say we had this, and then we had this. Now I can very naturally make a tree, right? It's A, B, C, D, E, F. I say, okay, I'm evaluating A and B first, I'm evaluating C and D, then I'm evaluating this, then I'm evaluating the result of these two, right? And I'm getting this, and then say that's a vertex, this is a vertex, and then I'm evaluating, this and this. It was a very natural thing. Like there's no other way in which this can be like, it's a very natural way to pair them up. So there's not a problem because this is how evaluation actually happens. But this one, which I'm referring to from Stanley's book, is very unique. Okay, but this kind of idea keeps coming up somehow, mysterious ways. Yeah, it's a very strange thing, but it's just very beautiful. So now, so let's just change a little bit. Be like this, and then we can do like this. Okay, so from here they make a tree. Now you will see they make a tree like this. So they say this is 1, 2, 3. Yeah, let me just make it more interesting. So I'll call this 1, 2, 3, 4, 5, 6, 7, 8. Okay. So they say like this. They say that, look, and okay, actually, it's not so counterintuitive. Oh, actually, yeah, now that I think about it. So we are going to make a tree from here. Okay. So just give me 1 minute. Just let me just trying to frame an explanation. Hmm. 3, 5 leaves. 1 second. So this 3 was 2, 4, and 3, 8, and 7. Right? Yeah. So we will make a tree with 7 leaves. Okay, we are going to make a tree with 7 leaves from here, because as you saw, the quadrilateral case was matching with this, and this was matching with 3 leaves, right? Similarly, the pentagon, which answer was 5, but this was matching with 4 leaves. Okay, so this would match with, just by analogy, just by pattern, this is match with a tree with 7 leaves, a tree with 7 leaves, right? So you see, actually, just like I was saying, this basically the reason I was giving, you can make it precise and get this bijection. I don't know why I never thought of this before. But the point is that, see, what did I say? That if you want to make a tree with 7 leaves, what are you going to do? You're going to start with the, obviously, you're going to start with the root. This is actually called root. Okay. You're going to start with the root. Then you're going to have 2 children, right? That has to have 2 children. Now you would have to tell the left child, okay, it's your job here to, let's say, produce 7, not 7, no, sorry, your job to, let's say, produce 5 leaves finally. Okay, and the right child is told your job is to produce 2 leaves eventually, and then stop. Once you're down to 2 leaves, stop. Don't, once you get to 2 leaves, stop. That's the kind of thing it is, right? Once you get to 5 leaves, stop. Okay, this is the way it's done, right? And this is the way this is the way the smaller cases are used to build up to the larger cases. Okay, if you look at the left, so I said that this is similar in this way, that once the triangle on base 1 comma 2 is made, then the problem gets divided into 2 sides. One is left side, one is right side. Let's say this is left side and this is right side, right? Then the left side is told you are responsible for, let's say, left side. You are responsible for so 5 triangles. You are responsible for some number of triangles, let's say 3 triangles. And the right side is told you are responsible for 2 triangles. And that's how it breaks up. Now the 3 and the 2 don't correspond to 5 and 2. But the point here is that the sum is 5 that side, and the sum is 7 this side, okay, which is the total number of leaves, and 7 and the 5 here is the total number of triangles, less than 1 because 1 is already used here. Okay, but the point is a break up in the same way. Okay, so my point being that this side is like the right subtree, and this is the main point. Point is that, look, this maybe I do it with black. This is like the root. Okay, this is like the root, and this side is the, you can say, right or left. Let's say that's a right subtree. This is the right subtree, right child, or the all the family of the right child, and this is the left child. Okay, so if you use that intuition, then it's not so hard to make a tree, because this naturally goes to this. There is no other triangle it will naturally go to, right? Now you can just continue the same thing. You can just continue the same thing, right? Once you are, so maybe I can do that with a different color. Okay. 1 minute. Okay, yeah. Yeah. Is this now you are here and here, right? Now you see, wait a minute. So then what happens then? So this is here and this is here. But how do you get a tree? No, you do get a tree, but will it be a binary tree? Yeah, so now you can just, yeah, so now you can just cross over, right? You can just cross and go to the next one. And you see every triangle will have two sides, right? Every triangle will have two sides. Wait, let me just complete this construction first. This seems a little odd again. So this and then, no, but then this goes to this. But then this just becomes a path. This is not even a tree. It's not a binary tree. Yeah, it's not, yeah, right. Uh-huh. Hmm. First one meaning? One minute. 1 second. Yeah, that's not a leaf, right? That's a root. Yeah, that's a root. No, then it will not work also, because you see the case for two triangles, right? That corresponds, or maybe you're right. The case for two triangles corresponds to three leaves, right? So two triangles correspond to three. So that doesn't, yeah. So that won't correspond. So 1 minute, let's see. So this is, no, but it's, first of all, the triangulation I've drawn is legal. And with the base 1, 2, I have to start with the vertex. And then if that has two sides, so it will have two children. And then, no, wait. So the triangle, no, but a triangle has three sides, right? And one of the sides, so the point here is a triangle has three sides, and one of the sides will be a parent, and the other two sides will be children. So in that case, but in that case, how will it work? If you suppose take this triangle in which one thing is a side and the, no, then 1 minute. One minute. Or is it something? Yeah, so what I have done is, 1 second. Oh, so yeah, so it is, so it is not so easy. It is not so easy. Actually, you cannot make a complete binary tree in this way. That's wrong. 1 minute. Yeah. So you see, you do get a tree, right? So it's not a, it's, yeah. So it's not a complete binary tree. So complete binary tree means, complete binary tree means every vertex should have exactly two or no leaves. So yeah. So we will have to loosen it a little bit. It's still binary in the following definition I'll make. So complete binary means that every vertex has 2 or no leaves. Okay, and binary, so there is something called a binary tree. Okay, binary tree, and that is not more than 2 children. Okay, not more than 2 children. Okay, so example for a so here the leaves are not such a good parameter. Here example would be like you can take this. So you can have 1 child. You can have 2, but you can't have 3. Is that right? Okay, so this is the condition. Okay, binary tree. So what I'm going to do now, so binary tree is fine, right? You can have 2, 1 or no children, but not more than 2. And again, we have left right distinction is there. So the point here is that given triangulation, you cannot naturally break it to a complete binary tree. So I'm sorry, yeah. There is a connection that's more complicated. That's even more complicated than what we've done. So we will not see that, okay, right now. But for a binary tree, you can easily see, because as I've already drawn, right, you start with the root and this will be like the left part and this will be right the right part, let's say, right? So from here you get a tree, right? What tree do you get? So this is the root. Let's say this is A, B, C, D, E. Then you can draw a tree. How? So from A, yeah, so from the root, you have the left A. Okay. Now, yes, you have to decide a direction. So, yeah, how do you decide the direction? So maybe you can decide a direction like this. You can face this side. So you can face this side, right? Face the side 1,8 inside, and that's B is on the right side. Okay, A is also on the right side. So then I'll draw A on the right and not on the left. So I'll draw one on the right. I'm just calling it A. And similarly, B is on the right. So B is the right child of A. Now remember, A doesn't have any left child, but that's not a problem because it's only a binary tree. It's not a complete binary tree. Okay. Similarly, C is on the left. Okay. Now if you, yeah, yes, someone is messaging. 1 minute. Okay, yeah, sure. Yeah. Yeah. Oh yeah, tomorrow also there is school. Okay. Yeah, so I'll just finish this. Not for, yeah, maybe some people have, yeah. Okay, so we'll just complete this. So from A to B, we are making, right? And then similarly, you see from C, if you again view, then it depends on how you view it. But so yeah, if you maybe you should view on the side only. So if you view on this side again, this side again, then again D is on the right, right? So D is on the right side. Right. So then again, you will make D on the right side like this. And then you make a E on the right side. No, but yeah, but E is again on the right, this thing, right? So it's again on the right. So you see, you get a tree, okay? And this is not a complete binary tree, but it's a binary tree, okay? So every triangle, and how many vertices is going to have? See, this will be exactly equal to the number of triangles. Maybe someone was saying, right? So this is actually number of triangles, right? So you get a binary tree with 6 vertices. Yeah. So every triangulation of 8, you get a binary tree with 6 vertices. And then this will be a 1-to-1 connection. Again, from a tree, you can go back. Okay. But then let me just say this the next time. Okay. Yeah, let me say this the next time because yeah, it's already, we have done a lot today. Yes. Let me just make another one and let me ask you guys to make a tree from there. Maybe that will be just a good exercise. Let's do that quickly. So I'll just copy something from the book so that I don't make a mistake. So this is a lot of sides. I don't know how many sides there are. You make another one. 1, 2, 3, 4, 5. Yes, yes, I'll name them. Yes, yes. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5, 6, 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. But 1, 2, 3, 4, 5, 6, 7, 8. No, I need 12 somehow. So you have to make. Yeah, so you have to make 12 of them. 3, 4. 12. So you have this, and then you have a triangulation. So I'll make the triangulation, then I'll name them. So this goes 1, 2, 3, 4, 5. Yeah, because in the picture, the triangulation is just there next to it. So I'm not showing the picture, actual picture. 1, so 1, 2, 3, 4, 5. 2, 3, 4, 5. So it'll be here. So this is how the triangulation starts. So they've chosen wisely. So I just want to do it because I can also verify my own thing if it's correct, thinking is correct or not. So then this is like this. So it is taking a bit of time. This I'll number the vertices. This comes here. Yeah, so remember this is a different side. So I can draw a bit. Doesn't matter. Yeah, perfect. So this is the 12 gone. And let's say that we can number it 1, 2, 3, 4, 5, 6, 7, 8. What? 12. This is C. And so obviously the root will start from here, but now you have to tell the tree. So take your time, do it, and see what you get. And press the base and you do left and right. Yes, yes, yeah. Because sometimes, yeah, not both the sides have new triangles. Not all three sides have triangles. Yeah, so that you can look at it from any side. You can look at it from E, let's say, yeah, and that looking at it explanation I gave is a slightly, I think, might be incorrect. So yeah, let's see. You will see and will understand. Yes, yes, yeah, but let's see if that gives us a bijection. Yeah, but let's draw a tree. Let's see. So you can describe the tree. You can say left child, right child, level, and so on. Hmm. Yeah, so let's call this A and B. So which one will be left? And Okay, so you're saying A is right and B is left. Okay, so let's see. Yeah. So, and B is left. Okay, yeah, that goes right with this. Hmm. No, no, but A has two children, C and E, but which is left and which is right? That matters. C can be right and E can be left. That one has to be very careful, right? Otherwise, it will not give us the same answer. You understand? Otherwise, you'll get a different tree if the left and right notation is wrong. Okay, so if you're saying C is right, are you going with C right or C left? C right. Okay, C right and E left. Okay, let's see. And then D will be right or left of E. No, 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 it cannot be a child of C, definitely, right? Because see, the children of a triangle, right? Yeah, yes, exactly. That you understand, yeah. But for it will be you're saying the right child of E. Okay. But why are you saying right and why not left? Because unless we know that we will not be able to from here go to a triangulation. That is so the rule has to be very clear why this is the right child. Because you will get some tree, but then you will not be able to go back to from a tree to a triangulation if the rule is not clear. So maybe this is, yeah. Hmm. But on which rule that matters. So for example, if you would have said that E is right, if someone would say that, if someone here would have said that they choose E to be right, then the answer will be completely different. Okay. Yeah, so that is the ambiguity, right? That is, hmm. Yeah, but then it's not a consistent thing, right? One has to, I don't know. Because if you look at it from the base, then if you look at A from the base of A, meaning this thing, then C should be left and E should be right. Started with E meaning Yeah. No, I don't know what is E's perspective. 7,76 or what? Uh-huh. No, but E's perspective, I don't understand. What do you mean? You have to say some side, right? E is not a side. E is a triangle. Yeah. Oh, sorry. That is, yeah, small e. That's right. So that's right. In the beginning, you look at it from small e's perspective, right? But then, as you come in, then you should look at it naturally from the base. So yeah. So but then also it's not wrong. So then you have to always look at it from opposite perspective. Ha. Then it's right. Is consistent. Yeah. So whatever rule you choose has to always be consistent. Then you have to look at it from this vertex perspective. Maybe you can say, right. Then if you look at it from the opposite, meaning the vertex perspective of the new triangle, right? Yeah. So you have to basically stick with a consistent thing, then it will be right. Yeah. So if you look at it from opposite perspective, maybe I'll use the word 7. I'll use 7. From 7's perspective, A is on the right and B is on the left. And so this is fine. Now, when you come to A, you're saying look at it from 4's perspective, C is on the right and E is on the left, right? Then when you come to E, you look at 6 and the D is on the right. So this is perfect. And this is actually the answer in the book. So they have also done your perspective. But but even if you look at it everything from the opposite, like I was saying, you go with this base and you go with this base. So the triangle you enter, you look at the base of that triangle, the parent there from where it's entering, then you'll get the opposite tree, right? But you should get a unique tree and you should have a clear rule, because if you have a clear rule, then you can reverse the process. Like then you can go from a tree to a polygon clearly, right? Then without seeing this picture also, you can draw this picture only from the tree. You see, that is important, right? To get a pairing, right? That for every triangulation, I'm getting a tree, and for that tree, I'm getting back the triangle. I can tell you the triangulation. So the tree has all the information of the triangulation. That should be there, and that will not be the case if my rule is not consistent. Okay, so, but your rule is consistent, so it is perfect. Okay, so what we have established is something new. So we have said that a triangle. So we have proved that triangulations. But you see, the idea was already clear. The idea was that how you break up into cases is the same on both sides, right? So triangulations with triangulations, triangulation of n sided polygon will correspond to, maybe I will use here n plus 2 because that's better to write. N plus the polygon is will correspond to a binary tree, not complete, with n vertices, not leaves, n total vertices. Okay, this we have proved. So we have proved a new thing. Okay, and then we will see that this is same as and basically we have already seen that, because we know that we know, but we have not shown it, but we know a pattern kind of. We see a pattern. So this is a question mark. This is done. All right. The question mark here is complete binary tree. So complete binary trees with how many leaves? So n plus 2 sides means n triangles, and we had seen that 2 triangles was 3 leaves, and so this would be n plus 1 leaves. And these you can check for small cases, we have already. But we have not yet shown a connection between these two things. And this is, I think, hard to show direct connection. Maybe we can show a direct connection between these two things directly. So somehow you have to take a tree which is not complete and you have to make it complete. Okay, as we thought about, this is not so easy maybe. Okay, And then there are other kinds of trees which also correspond to the same thing, but we will see. But you see, these things are slightly different. Yeah. Here meaning right or left? Which one? This one. Okay. This tree that we are drawing. Okay. Okay. Then. So then. Yeah. Uh-huh. Yeah. So let's just complete it. Yeah. Let's complete it first. So then you come to G, and for G there is a left child but no right child. No. Yeah, that's possible because it's not a complete binary tree. Okay. And then H has a right child. Why a right? Why is it not left? Uh, no, so with your notation, it should be left, right? No? Yeah. Mm-hmm. Why is it not right? From where are you looking? From 10. Oh, sorry. Yeah, it should be 12. Yeah, because that's perfect. Yeah, so it should be right. And in fact, it is right. Yeah, it's not left. Yeah. Okay. We have to, from the new vertex. Absolutely. Yeah. That's the most natural thing. Right. Correct. 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 That's right. So that's right. Okay. Yeah. Okay. Then what? Yeah. You want to go to a complete binary from here. Okay. Yeah. But that I don't know if that's very obvious. Yeah. That may not be very easy. So if we, from the triangulation, it is not at all easy, I think. Okay, because see, if you want to go to complete binary tree, then the point is that you have to only make the leaves of the tree, and this was something which I was also somehow stupidly missing, right? You cannot draw the tree. You have to means you have to only draw the leaves. Means that there are only n plus one leaves. How many vertices are there? We don't know. Well, there is a formula. It's very simple, but maybe you don't know. Right? Means it's not very obvious, right? If it has n plus one leaves, how many vertices should you have? Try to figure this out. This is a good home. This is a good thing to try. So basically, we need the connection with the right. So basically, if you I want to see, then maybe the triangles have to correspond to leaves somehow, right? And then you have to think. Is that right? Yeah. The triangles have to correspond to the leaves of some tree. If you want to go to the, so if you're talking about for a second, if you're talking about complete binary trees, then I shouldn't say much, but I don't know actually myself how one should connect. But the idea maybe should be that triangles should correspond to the leaves. Because n plus one leaves and n plus n triangles. right? There are n triangles, right? N triangles and n plus 1 leaves. So triangles and leaves, maybe we have to draw a connection, right? Somehow maybe we have to take these triangles, and these will be the leaves we begin with, and making the tree should be like making the polygon. You see that what I'm thinking, right? We will have a lot of triangles, these 10 triangles, and then we will have on one side, we will have 11 leaves. And then as you make the tree, and then say, as you club the leaves, you join it with parents as clubbing sort of. In the same way, you club the triangles, sort of. The edges or something, something this is getting clubbed with that, so these two will become, so maybe there's a connection, yeah. And then you shrink this to one triangle, and then you're reasoning again, there will be a beautiful connection. There is no end to this. Is a very interesting thing which you can just, now you can just think and you can do. There's a lot of, the more time you spend on this, you will get some new ideas. Okay, so maybe there is a connection, but it is not maybe direct. Okay, so think about it. These are the things that you can think and write. These are new things. So yeah, this connection is there. And also there is a connection, which maybe I will say this, I know, I think, which you can take any tree and you can, or rather, there's a connection between these two things, direct connection, that also you can think. Okay, so there are a lot of things to think. So number one question which you should do is, how many vertices will it have? This you can do for small case. Like if you make a tree complete, if you go to the previous examples we did, right, whenever we had 4 leaves, you would have seen that there is always 7 vertices. Whenever there were 3 leaves, there was always 5 vertices. You can go back and see. So there is a formula lying here. It's fixed for complete binary tree. If I tell you 100 leaves, there will be some number of vertices, fixed number of vertices. So there are some connections, but for arbitrary binary tree, there is no connection. It means there is no direct answer. So there are a lot of things here. Okay, you have to think. Okay, then. So I think we can stop. Are there any questions? If anyone, Unab, I think you're also here. If there are any questions for today's thing, you can please ask. And Sunday we will do a class. Sunday we'll do inequalities. This we will again continue maybe next week. Meanwhile, you can think about these things. Okay. Okay. So then there are no questions. Then we'll stop. Okay. Okay.